So yeah, this is work I've been working on for quite a long time, and it's yeah, I think I'm excited because a lot of things came together, and working on the slides it was kind of scary also how far I could go back, like looking at past presentations and stealing slides from pretty old presentations. So. But yeah, no, it's really rounding up a few things, so that's I'm happy about that. And so I thought I'd started with my my favorite website, which is NASA Worldview, and this is just a random day of first MPP measurements, and so the point is there are a lot of clouds. It's about 60% of the surface is cloudy at any given time. And clouds are very bright. And here you can see they're all white. But if I look in false color, so this is swapping the blue and the green with shortwave infrared channels where drops and ice crystals are absorbing. And so the bigger the particles are, the more absorption you see. And so because ice crystals are usually more absorbing or more bigger than liquid, then the ice clouds pop up like a pinkish in this way. So this is just then to illustrate a lot of ice clouds around. And it's not only just thin cirrus, but it's the tops of all these quite thick systems that are also ice. So ice clouds, they form when it's really cold, about -40°C when homogeneous freezing is happening. And liquid clouds are occurring below freezing, above freezing 0 Celsius. And there's this region in between 0 and -40°C where you could have ice clouds, you could have liquid clouds, supercooled liquid, or truly mixed phase clouds where really the two phases are combined. So to study ice clouds in this whole domain, you really also need to have a good filter on what is ice and what is liquid. And then if you're looking at ice, then you see a large variability of ice crystals, of ice properties. And so then I'm talking about the sizes and about the shapes. Liquid drops are nice because they're always spherical, but ice crystals can come in many different shapes. And this is just 1 minute of data flying through sort of random ice cloud during TC4. And within that small pocket of a cloud, you can see a lot of different shapes. Like these, we call them bullet rosettes. Basically columns sticking out of the center. There are some single columns in there, but also plates along with those. And also you see some of this big stuff there, but also many of these small crystals. Some of these might actually be measurement artifacts, but many of these are probably also real. So there's a huge range of size that's also involved in ice properties. Then looking further, zooming in further on these crystals, and these are crystals that are grown in the lab, you can see that the surfaces are usually not smooth. So you can see those roughness structures on these ice crystals, and those structures they change. They depend on, for instance, if you sublimate these crystals, then the roughness structures seem to be increasing. And so these also have quite some effect, at least on the optical properties, and maybe also on the physical properties. So there's a large variability of these ice crystals. So we do know a little bit where this variability is coming from, and simply said, in the lab, if you grow ice crystals and you change the temperature where they grow and you change the relative humidity or the supersaturation over ice, then you get different shapes. And so there's a lot of work done in the lab, but also comparing that with in situ measurements, and where it's kind of mapped what kind of crystals you get at certain temperature and at a certain saturation. And this is an example of that. However, that is really vapor deposition of so vapor condensing on the ice crystals that really make these crystals in the shape at a particular temperature and supersaturation. But then there's other processes going on, like aggregation of crystals where they stick together. There's movement of crystals, so crystals fall and some crystals are actually moved up by convection, and how fast they fall actually depends on the mass of the crystals, also a little bit on shape. So you get size sorting due to those processes. There's sublimation going on when the ice crystals are entering pockets where there's subsaturation, and then they can move into pockets where there's supersaturation again. So there's the cycles of those processes. They also can the shape can also depend on the nucleation mechanism and the properties of the ice nuclei that are involved. And there's a whole list I probably am forgetting. So, long story short, it's very complicated. And so we still have a lot of questions about ice crystals in natural ice clouds. So these are just some of them. So really, still, what is the natural variation of ice shape and size in ice clouds, and how do they depend on where the cloud top height is? How is it different between the cloud top and deeper into the cloud, and how does it depend on location, latitude, seasons, and so on. And so then the natural next question is, how well do models represent all this variability? Those, I mean, global models, but also just cloud resolving models, and even just the ice growth models that we can, so the most simple form of how to model the shape and sizes of ice. And then, so we can deduce some information about ice sizes and shapes and from satellite. But what are the biases on those retrieved properties caused by by ignoring the shape variations? So mostly we pick just one shape to model our ice optical properties, and that has some bias if the shape is changing. The last question I wrote down here is, so if we have a model, specifically a CRM, GCM, sorry, so it's predicting mostly ice masses. And so how can we relate those ice masses to the ice optical properties? So some models also try to predict other modes of the ice size distribution. And so how can we best do this translation, basically? So I decided to kind of make a sort of a long introduction and take a step back and go through some very simple relations, how clouds reflectance is calculated or is represented. And so the simplest form is this visible cloud reflectance, and in the visible ice is not absorbing, also liquid is not absorbing. So we get this very simple formula to calculate the reflectance. So this is in the two-stream approximation. So it really depends on the optical thickness and on this 1 minus g, where g is the asymmetry parameter of the phase function. And I will come back to that later. So we have a very simple formula, and then the optical thickness is really related to the ice water path and the effective radius of the ice. Where the effective radius of ice crystals is it's defined equivalent to the effective radius of drops, and it's related to the ratio of the mass or the volume, the bulk volume of ice over the total projected area. And so you can see that for an ice with a given ice water path, if you change the particle size, if you distribute that mass over more smaller particles, you increase the optical thickness and your reflection goes up. And then the asymmetry parameter is deduced from the scattering phase function. So this is phase function for ice in the visible. Here is the 22-degree halo that you sometimes see through cirrus. And the asymmetry parameter is really the first moment of this phase function, and tells you how much light is going in the forward hemisphere when it's scattered, and how much light is going in the backward hemisphere. And so when the G is 1, all the light goes forward. And you can see if it's 1, then scattering really it has basically no influence, because all the light is just going straight forward, and the reflectance will be 0. So for ice, so there's this large forward peak. So most of the light is actually going forward, but the asymmetry parameter is around maybe 0.6, which is very low for ice, and 0.95, which is very high for ice. And this is a huge range. If you plug in this in there, then the reflectance changes a lot using this range. Point to make is that really for ice is big enough to so that the scattering phase function, and that's also the asymmetry parameter, does not depend on the size of the ice crystals, but it does depend on the shape of the ice crystals.
Is mu not the cosine of the
Sorry?
Sorry, it's really trivial.
Oh yeah. Yes, no. This is the cosine of Stolicity. Yes. Actually, I wanted to change that, but I forgot. So sorry. So in the shortwave infrared, the reflectance is slightly more complex, and it depends on the optical thickness, the asymmetry parameter, and the single scattering albedo, which is basically the absorption absorption cross section divided by the extinction cross section, or 1 minus that number. And for ice, actually, approximately this what we call the co-albedo, 1 minus single scattering albedo, is approximately linear related to the effective radius of the ice. And then, so for ice clouds, the optical thickness doesn't change with wavelength from the visible to the shortwave infrared. So the optical thickness is the same. But in the infrared, the part of the optical thickness comes from the absorption, and this is basically how it's weighted between absorption and scattering. another thing to point out is that also the asymmetry parameter depends on wavelength, but it's mostly because the single scattering albedo, it's weighted by the single scattering albedo, so that you can actually relate the asymmetry parameter at different wavelengths to the asymmetry parameter in the visible in an approximate way. So anyway, so this is sort of the basis for the retrievals that I'm talking about, and also for some of the interpretation of the retrievals. Because so how we retrieve the size and the optical thickness is based on this, because as I showed, the reflectance in the visible, where I am not absorbing, doesn't depend on the size. It doesn't depend on the single scattering albedo. So you can deduce the optical thickness from that, and then from the short wave, where it depends on the optical thickness, but also on the effective radius, you can then deduce the effective radius from that. So if you have a measurement in the short wave and in the visible, so you're right here, then your optical thickness is 30 and your effective radius is 11. So you can kind of read off your retrieval from these simple diagrams. And this is done for MODS. So the MODS product has the optical thickness of ice and effective radius of ice. And this is just an average plot for the year 2000. Actually, also only for thick clouds, optical thickness larger than 5, and well, you can see some variation. However, for this retrieval, as I explained, the reflectances also depend on the asymmetry parameter. So we have to basically assume an asymmetry parameter to do those retrievals. And if we choose different asymmetry parameters, this picture becomes different, because of the reflectance doesn't only depend on the optical thickness, but also on the asymmetry parameter. So you get a different diagram if you pick different ice models with different asymmetry parameters in the visible. And that creates a bias. So if you have a bias in your asymmetry parameter, you create a bias in your optical thickness that is retrieved and the effective radius that is retrieved. And to show this in the equations, it's really, so the reflectance really depends on this tau times 1 minus g, where we sometimes call this scaled optical thickness. So for two different g values, if you keep that constant, then you get the same reflectance. So if you have a tau retrieved, this tau 2 at a certain with a certain asymmetry parameter assumed, and you can scale it to another asymmetry parameter by just using this very simple relationship.
Bastiaan,
yes.
Presumably the asymmetry parameter is different at different bands.
So that's what I come to now. So the optical thickness doesn't change. So the total optical thickness doesn't change, and it shouldn't change. So this is also true in the shortwave infrared, because this is about the scattering part of the optical thickness. So the optical thickness is the same in the infrared. It shouldn't change with G value. However, so if we scale the optical thickness in the shortwave infrared using this equation, then we are scaling the absorption part of the optical thickness, and that is not what we want to do. We want to scale the scattering part. So actually, we should correct that scaling of the absorption part using basically the inverse of this scaling. And as I showed before, so the 1 minus omega is related to the effective radius. So that is why we scale the effective radius to the inverse of the scaling that we apply to the optical thickness. And that is shown here. So these solid curves are calculated biases if we change the asymmetry parameter, and these dashed lines are just the scaling factors that are applied. So if we have other information about the asymmetry parameter, we can correct the optical thickness and the effective radius for that assumption.
But my question, I mean, G1 and G2 are the assumed versus what you then later on say you think it is. But my question was, the asymmetry parameter at different bands is different.
Yes.
Yes. That's,
yeah.
I was pretty sure of that. I just wanted to make sure.
Yeah. But they are different mostly because of the single scattering albedo. They're weighted basically with the single scattering albedo. They also depend on the real part of the refractive index. So this is an approximation, but yeah. So it's mostly the.
So I guess the reason could you go back one? Well, you showed the Nakajima king there. There we go. So those G's, that's your visible G or your shortwave infrared G?
That's the visible G.
Okay, all right.
Yes. But so it's really this scaling you do with a visible G. So you don't have to know the G at different wavelengths to do this kind of scaling. Ping Young was here last week, and he in one of his talks he showed a different kind of scaling, which does use the G at the shortwave wavelength and the omega. But actually, so if you do if you look at the outcomes, basically, this scaling actually seems to work better than the scaling that he was talking about.
I think you were talking about long wave scattering, though.
No, that was
a different part.
Maybe if yeah, well, it was about all wavelengths basically. It's this similarity parameter, which is also valid in the shortwave. Anyway, where was I? So I said that the scattering properties depend on the shape of the ice, and here I break down the shape of ice in two different scales. Basically, there's the macroscale, which is the general shape, like the habit. Like this is a bullet rosette habit. This is just a column habit. This is an aggregate of plates. That's the largest scale. And then there's the mesoscale, which is really the aspect ratio. So how long this column is, or how long the arms of the bullets are, or how flat the parts of the aggregate of plates are. And then there's the microscale, which is this distortion or roughness structures that are on the crystal. So these are the three different scales. And so this shows phase functions for smooth particles and for very roughened particles for different habits. So this is really focusing on this general scale. However, if I would to order this, what is most important, then actually I would turn it around, and really the aspect ratio of the components of crystals is very important. And the level of distortion or roughness is very important. However, the general scale, or the general shape, so the macro scale, is least important. And what I mean is that, so this is an example of that. So where this is a pretty old paper where they made different bullet rosettes. So they made all these different complex crystals where they basically stuck these crystals together. And if you deduce if you calculate the phase function of that, you can basically always come to the same answer. So but you do get to a different answer if you change the aspect ratios of these crystals. So you can use the simplest form of these crystals actually as proxies for all of these other crystals. And the simplest form of ice is really an hexagonal structure, because that is where the water ice maze is forming an hexagonal structure. So hexagonal plates and columns are really the fundamental shape of these crystals, and you can use simple hexagonal plates and columns as proxies for more complex crystals. And that leads to a practical model where you have just two parameters to change. You change the aspect ratios of these crystals, and you change the roughness or distortion, which is a parameterization of this roughness structures on there. And you don't have to change the shape, which is also not a parameter that you change. It's not a number. You're gonna change bullet rosette to plates in a number sense. So this is my basically practical model that I apply to this problem. And then if you look at the asymmetry parameter, then it scales really with the distortion, roughness. So if you make rougher and more distorted particles, then the asymmetry parameter goes down. And if you make particles with higher aspect ratios, so flatter plates or longer columns, then the asymmetry parameter goes up. So if you know the aspect ratio and the distortion of your proxy particle, then you also know the asymmetry parameter in the visible. So, so we cannot get this information from MODS measurements, but we do get this information from multi-angle polarization measurements. And there was a polarimeter in the A-train, which it's a French instrument, Polder, on the Parasol platform. It moved out of the A-train. It actually burned. It exited or whatever. So it's not anymore, but it was in the A-train for about 5 years. And so we can combine those measurements with the MODS measurements, and then my retrieval of these proxy, the shape of these proxy crystals is very simple. It's so the polarized reflectances, just as the phase function, also depends on the aspect ratio and the distortion of these crystals. And so, so with those multi-angle polarization measurements, you basically sample those polarization structures. So, by matching the multi-angle polarized reflectances that are measured with the simulated polarized reflectances for different aspect ratios and distortions, I can retrieve the aspect ratio and distortion, and also retrieve the asymmetry parameter from that. So I applied this quite a long time ago on simulated measurements, using those complex habits that I showed before from Ping Yang's group. And so I can retrieve the asymmetry parameter from that within about 5% or so. And I also retrieve the aspect ratios of components of these crystals, and also the level of distortion. Another thing, nice thing about polarization is that liquid drops and ice look very, very different if you look at the multi-angle polarization signature. Because for drops you see the rainbow, which is very highly polarizing. So so we can filter out really any pixel that has some amount of liquid in them by looking at these scattering angles. And if we see anything that looks like a rainbow signature, we throw those out. So it's very well filtered for any liquid clouds in the pixel. So I applied this this retrieval to polder measurements from 2007. So that's on a 6x6 kilometer pixel level. There are filters applied for the goodness of fit that I get. I only look at thick clouds now, optical thickness larger than 5, and I apply these very stringent phase flags. So only looking at ice clouds.
So everything's single scattering, right? It's the top of the clouds. So
Oh yeah,
why do you care about why do you care that tau is greater than 5?
Because there's other things scattering, like there's radii scattering. The surface has also some influence, especially so on
surface.
Yeah. On the ocean you have glints. If you so I did retrievals for thinner clouds, but yeah, to be safe, I applied this filter. So, but yeah, I end up with quite a lot of retrievals, so a lot of statistics. So looking at the average, so my average asymmetry parameter in the visible is 0.75, which is very similar to what they now assume for the MODS kind of retrievals on a global scale. On average, I see mostly plate-like crystals everywhere, and which are very highly distorted. So, so this distortion parameter of almost 0.7 is it's a parameterization, but it really shows that it's very highly distorted, almost maximum distortion, basically. And which is also assumed for the MODS retrieval. So it's consistent with MODS retrievals, which is not a surprise because they are also based on polder measurements, not these retrievals, but just global average measurements of polarized reflectances. And so now I can do this correction, because for every polder pixel I have the average effective radius and optical thickness that's retrieved from MODS, and I can apply this correction to the effective radius. So that is shown here. Nothing, it doesn't really change the average that much, because the average of the MODS retrievals already is close to the average that I retrieve. But I do end up with these maps of effective radius, asymmetry parameter, the distortion, and aspect ratio. We can stare at these maps for a long time, but actually, so many features that you see in these maps are because of the clouds are different, and especially because the clouds are at different heights or different temperatures. So a better way to look at this is really as a function of cloud top temperature. So these are averages for different cloud top temperature bins, to Kelvin bins. And so the effective radius, the asymmetry parameter, distortion, aspect ratio. And some interesting things you can see that, so these ice crystals are very small for very warm cloud top temperatures. Then they increase as the temperature goes down. There's this maximum right here, and then for colder temperatures they start to decrease again. Around the same temperature here, you see that the asymmetry parameter starts to change. So for cold clouds, it's very low asymmetry parameters, and that's mainly because the distortion is really high. And then for these warmer temperatures, the asymmetry parameter is higher because the distortion is lower. The aspect ratio changes. It's quite a small range, but so there's not much change, but there's this very interesting dip around 260 Kelvin. So and these are over ocean, and so this is over land, and not so much is changing with the asymmetry parameter, distortion, aspect ratio, but in general the sizes go down, as you can see. But the same general behavior is seen. So now we can try to start to understand these relationships that we're seeing. And we can understand these sizes maybe by the growth rate of these crystals. And so growth rate can depend on a lot of different factors, but in approximation, they depend on the supersaturation over ice, and they depend on the saturation pressure of ice. So that is really how much ice condenses on the surface at a certain level of supersaturation. And this vapor pressure, saturation pressure over ice, that's an easy calculation from the Clausius-Clapeyron formula. And then the supersaturation over ice is taken from the measurements shown here. So these are supersaturations measured in ice clouds, actually in pretty thick ice clouds. And they always, they're supersaturated, of course, but they are below the water saturation at that temperature. Oops. So what this leads to is that the saturation pressure of ice, it goes down as you go to colder temperatures. So the growth rate decreases, which is shown in these plots from Bailey and Hallett. And then at the warmer temperatures, we can see that actually the effect that the supersaturation increases as you go to colder temperatures. That leads to an increase of the growth rates. So there's this peak, which is on these laboratory measurements is around minus 15 degrees Celsius. It is a peak in growth rate. However, these simulations, or these measurements, actually laboratory measurements, they assume a water-saturated environment. But in fact, we have a lower saturation in real ice clouds. So what I did is I took this formula here, and I took this parameterization that they provide, and I just calculated this growth rate. And what I get then is this, I hope you actually see it, is this gray line, dotted line right there. And it really tracks the variation in size very remarkably well, I think. And then also, if we do the same thing for land, over land, then yeah, we see that it fits pretty well. However, over land, this peak is slightly colder temperatures, and we get that if we change the supersaturation slightly, if we make it slightly less humid over land, which is probably the case over land, then if we change that supersaturation, we actually increase this or decrease this the temperature where this bump is. So I think, yeah, we can explain this variation in size just by the simple picture of supersaturation and saturation pressure, which is maybe remarkable because, yeah, there's all these other secondary effects that are going on. So next, I wanna talk about the aspect ratios, and especially this dip in aspect ratios that we can see here, because aspect ratio is also predicted by some theory, and jumping straight to this plot here, this is showed what is called inherent growth ratios, which are actually deduced from laboratory measurements. But it's used in models that try to predict the aspect ratios at different temperatures and also different humidities. And the most robust thing, I think, of these inherent growth ratios curves is this dip around minus 15 degrees Celsius. What happens here, whether you get plates or columns, that's a bit, it probably also depends on the relative humidity and other factors. So that's why they actually have two lines right here. And it's probably straight, but that's very really uncertain. However, if I take this curve and I overplot it on my retrievals, I get exactly the dip in aspect ratio where this dip in inherent growth ratios are. So that really matches also very well to the observations. So the observations match well with this simple theory. So again, this is quite remarkable because of all the things that are going on, it could be going on. So I think the conclusion is that really at the tops of these clouds, you have this simple picture where ice crystals really grow from vapor deposition. And then all these other things like aggregation and size sorting and rhyming and everything, that is really things that are mostly happening deeper into the cloud. And so at cloud top, we can have this simple picture on average. Mind you, these are averages of a lot of clouds, of course. So maybe if you look at different cloud types, we can see differences in these pictures. So I haven't talked about the asymmetry parameter and the distortion yet. And for that, I want to plot them in a different way. So this is the asymmetry parameter as a function of the effective radius of size. And you can see that the asymmetry parameters are highest for small particles and that they decrease with effective radius. And that's mostly because the distortion increases with effective radius. And also the aspect ratio changes a bit. So this is for warm clouds, and then for cold clouds, so colder than the homogeneous freezing level, we see the same picture. However, this transition from undistorted crystals to very distorted crystals happens at a smaller size. So one caveat is that these retrievals are not independent because this effective radius is corrected for the asymmetry parameter. So part of this behavior actually you get from this correction. However, I want to make the argument that this is actually what we probably expect, also given new laboratory measurements. First of all, so ice grown in cloud chambers and in laboratories are studied with an optical probe. That also sees roughness or distortion of these crystals in a similar way that my retrievals do. And what is found is that they deduce this complexity parameter, which is actually you can relate to this distortion that I'm using. This complexity parameter increases as at a certain temperature as you increase the supersaturation, basically the available water vapor for these crystals, and also just using the growth rate as a variable, you can see that the roughness or this complexity increases as you increase the growth rate. So faster growing particles grow rougher or more distorted. So you would expect the distortion to increase with particle size, as we also see. Looking at sort of more larger scale distortion parameter is done here, where they use these images of crystals, and they deduce the complexity parameter from these images, where these crystals are very non-complex, and these crystals are more complex. So they deduce a complexity parameter from these measurements. And then what they see is that the smaller particles are mostly simple, and as the particles become larger, then you get into more complex crystals. And there's this transition. And this transition happens at larger particles at warm temperatures than compared to colder temperatures.
But isn't this isn't what you call macroscale?
It
you
is.
were talking about microscale in the previous
so
slide?
that's a very good question. Yes, it is macroscale. However, so I haven't really talked about that, but this distortion that I use, it's a very general parameterization. So it's not only distortion of the small scale, the microscale structures under the crystal, but even if you make a crystal that is like you make a nice hexagonal crystal and you start to like bang it and make it more complex like this, then it actually has the same effect. So we can see. So I think what the retrieval, it's a convolution of this small scale distortion and this macroscale distortion. So that's an open question, like what is really going on. However, so this does fit really well with what I'm seeing also. That for warm temperatures, you have these transitions at larger crystals than at colder temperatures. So actually what they did is they parameterized this. So they have a very simple formula to fit this transition, and they fit this transition size, and then they plot it as a function of temperature. So you can see that transition size increases as you go to warmer temperatures. So I thought, like, wow, this kind of looks like what I'm seeing. So I took exactly the same formula, but now the transition size is the effective radius. And so this is just an example of different temperature ranges that I plotted. But if I do this at quite a high temperature resolution, I see this transition size nicely scale with temperature, very similar to what they see. So I'm not saying we're really seeing the same thing, because there's also the roughness and so on, but it gives you a parameterization of this distortion or roughness or whatever as a function of effective radius and temperature.
The transition is 50%. Is that what is the transition radius refer to? Is it the 50% line on the top?
It's this. So it's this formula fitted to these.
Oh, I see. It's just something. It's part of the curve. It isn't something simple.
Yeah. So actually, I normalized this by the maximum. That's not on there. I normalized it by the maximum, which is 0.7. Yeah. So that's a good point. I should add that to this slide. But anyway, so it really seems to fit nicely. So finally, so this is relevant because current ice optical models, so this roughness or distortion, whatever, it's not. We know that we should apply some distortion to these crystals, but it's really not known how much, and it's not known how it depends on temperature or size or anything. Well, before now. So really, what has been done is it's not applied, or it's a single value applied, and also if you look at the symmetry parameter as a function of size, that many of the models actually they have a symmetry parameter that increases with size, and that's because the shape changes. So you get more flatter plates, for instance, added to this mixture as you increase the size, and that's why the asymmetry parameter goes up. But if I overplot my retrievals, then you really get the other other behavior. So it's really the other way around. And this is important because, so we go to this one. So if we go back to this equation again, so you had the optical thickness written like this, and what is often done is that this part is called the mass extinction coefficient. So if you just multiply with the ice water path, then you get the optical thickness. However, we also should take into account this 1 minus g. So I define a scaled mass extinction coefficient by just this parameter times 1 minus g. And if you plot that, then for the models that have a symmetry parameter that do not change with size or that actually increase with size, then your smaller crystals will have a much larger scaled mass coefficient than the larger crystals. So your model is very sensitive to size changes. However, if you applied the retrievals that I got, then you get much flatter curves. So your model is much less sensitive to changes in size. So if you put this in the model, the model will be less sensitive to size. And also, if you use this for a retrieval, and actually the retrievals for let me go back. So if you retrieve a small size and you use this symmetry parameter, your bias high. So you retrieve a size, but the bias is positive, is high. So this kind of squeezes your the range of effective radius that you retrieve. So that was it. So yeah, so one general conclusion is that on average, so these ice optical properties at cloud top seem to be remarkably consistent with this basic ice growth theory. And I think that other things like aggregation, rhymings, and so on is really more important deeper into the clouds than at cloud top. So we can maybe use these models that are based on this theory to retrieve or to model the crystal properties at cloud top. And then for deeper layers, we should take into account all this stuff. So this retrieval is now applied to 1 year of polder data, but I also apply this. So this is applied to RSP or airborne RSP measurements. But I plan to apply to the whole polder record. But it also can be applied to future missions, for instance, the PACE polarimeters, and hopefully also the far future mission of ANCCP. So, thank you.